Post-tensioning design options. This presentation gives a brief historical background in development of design methods for post-tensioning members, then outlines the different procedures that are used now, application of each of these methods, and the differences in their features, building code treatment of tendon when it comes to different design methods. Let me start with a brief historical background. It helps in appreciating the different methods. In 1800, the benefits of post-tensioning was recognized in Europe, but its application was limited to special structures. Why? Because the hardware was very complex and the method of analysis was very complex. Not everybody could do it, and also not everybody could execute it. So it was limited to special building structures of significance or bridges. Around 1920, Freycinet came up with this device that we are looking at it at the right. This is an anchorage device for multi-strands. This greatly simplified the construction, but the method of design was still complex. So construction increased, but nothing like what we have today, because you needed to be knowledgeable in going through the design. It was in mid-1900, 1955, 1963 actually is the well-known paper by T.Y. Lin that he introduced the load balancing method of design, which greatly simplified the design procedure, and it resulted in increased application of post-tensioning in common building construction. In 2022, not far from here, the straight method was introduced, which even further simplifies the design of post-tensioned members. I will give you a very brief background of each. Now, these are the three methods. Here I am showing in the image the basics of load balancing, where the post-tensioning tendon is extracted and the forces it applies is then applied to the member. And that the applied forces of the post-tensioning added to that of gravity and other loads will reduce to somewhat smaller applied load. Now these are the three methods. All three follow three steps. They have a service condition, which is deflection, cracking, vibration. They have a safety analysis section, which is safety against overload. And they also have a section on transfer of pre-stressing, that at jacking force there will not be rupture of post-tensioning. There are other objectives such as compliance with the governing code, economy in design, and otherwise, which are not a focus of this presentation, although all three of them meet the requirements of ACI 318 and the European Code. All three meet the objectives and the requirements of the code. Now, what is the primary difference between the three methods? One is the complexity in design steps and economy in design, and correlation between design and the response of the structure. In other words, the last one is very important. How closely the design predicts the response of the structure under load. That depends on the method. And of course, how economical the design is going to be, again, depends on the method, and also there is this level of complexity. But all achieve the three requirements of serviceability, safety, and transfer of pre-stressing, and meet the requirements of ACI and the European Code. Now, what are the distinguishing features of the three methods? Starting with the straight method. In straight method, which was described in detail in this reference, the post-tensioning is viewed as an applied load for service condition and is viewed as an applied load for safety condition. So post-tensioning is viewed as a load. In load balancing design, post-tensioning is viewed as an applied load in service condition, but as a resisting element in safety. In other words, in load balancing, for service condition, post-tensioning is a load, like dead load, live load. In safety condition, post-tensioning is a reinforcement, not a load. That is the difference between these two. The comprehensive method, post-tensioning is a resisting element in service condition. In other words, post-tensioning is like rebar, with the difference that it is a rebar with initial force. That differs from the other two methods. For safety, post-tensioning is a resisting element, is a rebar again. When I say rebar, acts like rebar. In this comprehensive method, it acts like reinforcement all along. Now, the references for each of these is given down here. Now, what is the application of these methods? The straight method is very simple to apply. Doesn't require extraction and separate consideration of hyperstatic or secondary actions from pre-stressing. I know a lot of our colleagues are uneasy about secondary or hyperstatic moments, and to extract them and take them into account separate from other loads. This method doesn't require that. The question of hyperstatic moment or values doesn't come up at all. Now, does it mean that it ignores it? Absolutely not. It is already included in the analysis, taken into consideration as required by ACI, but you as engineer do not have to extract it explicitly and view it as a separate entity. It's already there. The outcome is that it is slightly less economical when you compare it with the other two methods. When I say less economical, in some instances, not so much in ACI, in some instances you end up with using more post-tensioning. I would say not so much in ACI 318 because in many instances the amount of post-tensioning arrived at using ACI 318 is from serviceability check, not the safety check. And it is when you go to safety check, you will find out you have a little bit more than what you need. The proof of it is that you not always end up with added rebar. Once you do serviceability check and minimum rebar, you already in many instances have satisfied the safety. Anyway, the load balancing requires basic knowledge of post-tensioning, which you do not need in straight method. It requires explicit extraction of hyperstatic actions. Typically software is used, and it is slightly more economical than the first one. The comprehensive method requires in-depth understanding of post-tensioning, is applicable to projects where time-dependent deformation is critical, such as segmental bridge construction or cable state constructions, or other constructions where deformation plays a great role. Then you have to use this method. Practical designs requires specific software, not amenable to simple hand calculation. Definitely not. The design can be concluded without the explicit extraction of hyperstatic actions. You really don't need to consider that there is something like hyperstatic actions and pull them out and put them in your load combination. But since ACI has its own limitations, and if you want to follow the letter of ACI in your safety consideration, you still have to pull the hyperstatic out in this case, but not in the straight method. Now I'm going to give you the background, what is really the difference between the three in one step deeper. Now, the figure here shows a member which is post-tensioned, and it has a rebar. And here are the forces that this post-tensioned tendon is applying to the member. Initially, the tendon force in service condition is is P. P is the force in tension, and the common practice is to assume that rebar has no force initially when you cast the concrete. So here, if I make a section, rebar has 0 force, post-tensioning tendon has force P in it. Good. As load is applied and the member deforms, both the tendon and rebar stretch. The rebar will stretch when you apply load, tendon will stretch. The stretching of tendon and rebar results in change in the initial values of the force in them. Obviously, yes, when they stretch, the force in them will change. So this is figure A, shows the initial condition, 0 and P. Now, the figure shows a segment of rebar. For evaluation, we look at these two segments. In service condition, the force in rebar is generally assumed 0, and the force in tendon is assumed as P. That is what we have to start with. Now, at strength condition, the deformation of the member results in force F in rebar. And for safety, we take advantage of presence of rebar. We put rebar with 60 KSI or 460 megapascal force to provide resistance. Now, for bonded tendon at similar location to rebar, the stretching will be the same as rebar. Imagine you have a bonded tendon next to rebar. The stretching will be the same because both of them are steel. If one results in stress F, the other one must also have its initial force P changed by F. Now, pre-stressing steel and rebar being both steel in material, the increase is in similarly located tendon will be the same as F. So in summary, at ultimate limit state and bonded tendons, the gain in stress is similar to rebar. I'm dwelling on this excessively because that is what makes the difference between the three design methods, as we will soon see. Now, in summary, the increase in rebar stress will be the same as increase in tendon. It is the recognition of increase in tendon force at ultimate limit state and allowance for it in design that differentiates the three design options. Now, let us review the three design options. We go to straight method, which is the simplest. For service condition, the force shown in A is assumed. Rebar has 0, tendon is P, that is service condition. For safety condition, the force in diagram shown in B is assumed. This is assumed. The tendon force is P. You see, it was P in service. It remains P in safety, remains the same as in service. But rebar goes to F. What is the difference? In this method, we do not account for increase in tendon force in safety. It is the same. That simplifies the design dramatically, as we will see shortly. The presence and contribution of force F in rebar is accounted for. That is for strength. This is accounted for. Typical load combinations are, that is important. For service, we have 1 dead, 1 live, 1 PT. For safety, we have 1.2 dead, 1.6 live, and concentrate here, 1 PT. Typically, when you do load balancing, you have 1 hyperstatic. And that is why we have to extract hyperstatic, because ACI says you have to account for hyperstatic in safety. But when you put 1 PT, this already includes the hyperstatic, because this force here, which comes from the service, includes the results in the hyperstatic with factor 1. So this is ACI code compliant, but very simple. You don't have to go through the hyperstatic calculation. The inclusion of PT as applied load in safety condition accounts for presence of hyperstatic action with factor 1. Now let us go to load balancing. In load balancing, in service condition, the force shown in A is assumed 0 and P. This is the same as the previous one. We assume rebar has 0, tendon has P. For safety condition, B is assumed. For safety condition, we assume rebar will stretch, and the stretching of rebar is transferred, or is replicated is the right word, replicated also in tendon, depending on whether it is bonded or unbonded. There will be different amount of allowance for stretching of tendon. The presence and contribution of force F in PT tendon is accounted for in strength limit state. Now, typical load combination in ACI is this dead live PT, that is the same as simple scheme. For safety, this is changed to hyperstatic instead of PT. That means we have to apply this. The way ACI means is that for safety, you apply this to the structure now, and you calculate a set of forces in the member as a result of this, and you call them hyperstatic, and you put them here. Hyperstatic is HYP is the hyperstatic action. The method requires explicit evaluation of the hyperstatic value. Now, background to differentiating. Now let us go to the last one, comprehensive method. In the comprehensive method, in service condition, the contribution of rebar is accounted for in location and magnitude. Now, remember, in the other two schemes, for service condition, rebar was assumed to have no stress. Its presence in providing stiffness, in resisting deflection, was ignored. In this scheme, rebar will add stiffness. Rebar will resist in service condition deflection of the member, deformation of the member. Now, when we go to strength condition, the increase in rebar is accounted for in the safety condition. Typical load combinations for service are dead, live, PT, and rebar. For safety, this is for code compliance. In reality, you don't need this. You just put the PT force. But the way it works, ACI, if you want to follow the text of ACI, ACI says you include hyperstatic. So you have to extract it to satisfy ACI, but it's really not needed to get a safe solution. It is implicit in the solution. Now let us look at the treatment of the code when it comes to accounting for change in tendon stress. ACI and EC2, the European code, both allow for increase in pre-stressing force at limit state, but allow for it differently. depending on the configuration and parameters of structure, the following are the approximate limits in increase of stress. ACI can allow, or the allowance for bonded can be as high as 60 ksi. It depends on a number of parameters, but it can be as high as 60 ksi. For unbonded, it can be as high as 43 ksi. Again, it depends on a number of factors. EC2 for bonded allows 110. Compare the two. For the same structure, EC2 allows almost twice for bonded. For unbonded, EC2 allows only 14.5 compared to 43. What is going on? How come across the ocean there is such a difference in understanding of how structures behave? It implies, as far as I'm concerned, that there are other elements. Here we prefer unbonded, 43. There they prefer bonded, so they put 14.5. Anyway, that is more comes the elements and the forces behind the code provisions in each locality, how to push the provisions. There's a notable difference between the allowance of tendon force at strength limit state. This leads to the thought that the phenomenon is either not fully understood or is given execution, or a given execution style is promoted. So, in summary, I started with a brief history of design development, talked about different design options, straight method, load balancing, and comprehensive. Talked about the application of each, that I want to take advantage of the moment and say, if you have a small project, use a straight method. It's very simple. You don't need to go through the hassle of hyperstatic bones. The benefit or the saving is not worth the effort. I talked about the background and basis of development of each, and I talked about the building code treatment of each. That brings me to the conclusion. The material presented was taken from a chapter of this book here. Thank you for listening.